Welcome to this video on how to use Mathematica in multivariable calculus. Here, we will see how to visualize level curves defined by two variables functions. We will also see how to visualize level surfaces. It is our second video of this series of videos of multivariable calculus. Here, we have the list of exercises and some definitions we will use later. And one way of visualizing functions of two variables is by their graphs. We will see these visualizations later. Now we will focus on the level curves of a function. Before starting, let's consider the following definition. The level curves of a function f of two variables are the curves with equations f of xy equals k, where k is a constant that belongs to the range of f. It is the set of all points in the domain of f at which f takes a given value k. In other words, it shows where the graph of f has height k. This can be thought as the traces of the graph of f with the horizontal planes z equals k, projected on the xy plane. So if we draw the level curves of a function and visualize them being lifted up at the indicated height, then we can mentally piece together a picture of the graph of f. The Mathematica function that is used to construct level curves is contour plot. So let's type it. The second entrance there in the pop-up window that appeared. Here it is, contour plot. And let's go to the eye that appears there, and it directs us to the documentation center. There it is. Contour plot generates a contour plot of f as a function of x and y. This is the level curves of f. Let's see how it works with the first exercise. Remember, if you scroll down, you may copy from the examples and paste and adapt the example here in our notebook. So here we have the function is 25 minus x squared. So let's start by typing contour plot. It is already there in between square brackets, 25 minus x squared. I forgot the x. Separated by commas, the range of variation where x and y are defined. -2, 2, and y, let's use the same. Here it appears a message, and it says that endpoints for x in 2 are the same. I didn't put the negative sign. And here they are. If we start here, we see that these are straight lines parallel to each other and parallel to the y-axis too. More precisely, as the set of pairs x and y belonging to the domain of f, such that 25 minus x squared is equal to k, and k is less than or equal to 25. Remember that in the video of domain and range, the range of this function was set less than or equal to 25. So formally, we may write this result as text. Here, below that drawing, we use the shortcut Alt and 7 at the same time to generate a text cell, and there we type the following: level curves of f equals, it is a set, so it goes in between curly braces, xy belonging to R square, not R square, belonging to the domain of f, that the domain of f is R square, but precisely it is belonging to the domain. Here is the belongs to symbol. Such that 25 minus x squared is equal to k, comma, and k less than or equal to 25. Let's adjust here in italic. Okay, so here we have written the set that defines the level curves of f. Well, so let's interpret it. As the curves, in this case, straight lines, are drawn where f takes a constant value, this is the height of f, Mathematica indicates that the highest values of k with clearer colors are those that are here in the middle. This corresponds to k equals 25. This one to 24.5. If we want, we can erase the colors and add those values. For this, we will need two options. So let's copy and paste below. And one of the options that is legends. There it is. Automatic. With this option, we add the values. And the other option I was referring was adding the values where the curves are shown. We can do this like this. I will remove this option and I will add contour shading. There it is. And in contour shading, I will choose none. So no colors. And contour labels. And in contour labels, I will add true. Verdadero. So with true, I see the curves that are straight lines, and on each level curve, I see the value of k. Well, but as we said before, the contours can give us an idea of how the graph of f is if we visualize them at the corresponding height. For example, there are two lines of the level curves that have value 21.5. That are these two lines, one on the right and one on the left. These lines are obtained by intersection of the graph of f with the plane z equals 21.5. This results in the equation 25 minus x squared, that is the equation of the function, equals 21.5. Let's ask Mathematica to solve it. And for solving an equation, we use the command solve. If you are interested in how solve is used or its details, you can click on the eye and you go there to directly to the documentation center. I will just use solve to solve this equation. So 25 minus x squared. The equation in Mathematica is constructed with double equal. 21.5. Shift and enter. And here we have, as we see, there are two values of x. X equals to 1.87 to 2 decimal places, and x equals to negative 187. These are the straight lines in the plane z equals 21.5, and you can see them here where I put the cursor. Now, let's visualize one of these curves in 3 dimensions. How? Using parametric plot 3D. So if we start typing parametric plot 3D, there it is. We click there and we go to the eye, and here we have it. Parametric plot 3D produces a 3-dimensional space curve parameterized by a variable u, which runs from a minimum value of u to a maximum value. In this case, the curve will have x value constant and equal to 1.87. But to be precise, we should use the exact value of x. This is the one obtained from making x the subject in the equation 25 minus x squared equals to 21.5. In this way, one of the solutions will be, we can do it mentally. One of the solutions for x is 25 minus 21.5, all that square root. So when parameterizing the curve, I need a parametric plot 3D in between brackets, the function parameterized, and the function goes as a list. So the parameterization here, we will use y as parameter, and I said the value of x will be square root, can do it mentally, of 25 minus x squared. Sorry, 25 minus 21.5. I'm trying to make x the subject, so it is 25 minus 21.5 equals x squared. Now, making x the subject, it is square root of 25 minus 21.5. So this is the constant value x. Y is a parameter, and z is equal to 21.5. Here, the parameter that ranges in between -2 to 2. So the curve we have recently defined should be visualized in the same region for x and y defined before. This is from -2 to 2. But we should add the range for z, and we do this with plot range. Plot range, and as a list, I add the 3 representation ranges. For x, from -2 to 2. For y, the same, -2 to 2. And pay attention to z, as we have maximum value 25, and here Mathematica is showing us from 20, let's say 21, we can put here 20 to 25, and I think it will work. So Shift and Enter, and here we see that line, this level curve, the one that has value 21.5. Here it is on in the space, in the 3D space. So that line is the intersection of the graph of f, that we will see later, with the plane z equals 21.5. If we repeat the same process to visualize the rest of the curves, we will have a panorama of the graph of f. Of course, Mathematica could automatically do this, generating a list of level curves. These curves will result from the equations 25 minus x squared equals to k, not equals to a specific value as we did here, but equals to k, where k is in between, let's say, 20 and 25. 25 is a maximum value k may take. And we could also increase those values of k in steps of 0.5, for example, starting from 20, then 20.5, then 21, and so on. And Mathematica uses the command table to generate lists. Let's see how. So if we type table, we click here on the eye, and it says it generates a list of n copies of expression. And as I said that I want to increase the value of k in steps of 0.5, I will consider the fourth entrance that says uses steps di. So let's see how. Here we will start generating a list for the level curves. I will define this list levels. So levels will be a list. I use table, brackets, and here I have to put the parameterization that define the curves. Before doing this, here I will solve the equation I used before, but instead of 21.5, I will use k. And I will specify that the variable is x. Otherwise, Mathematica could solve it for k rather than x. So Shift and Enter here. And here I have two values, the positive one and the negative one. So now I will define the list of curves parameterized by x equals to 25 minus k, the positive value, and I should also consider the negative one. So I will generate a list of level curves, and we will start defining them as follows. So the value of x will be square root of 25 minus k. The parameter will be y, and the value of z will be k. Well, these are the curves that have the positive solution of x. Now, as another list, I will add the same but with the negative values of k. So I copy and paste. And here I put negative. But remember that all this is the first argument in table. Remember, let's revise the syntax of table. Expression, the expression here it is. The expression I want is the list of level curves, the parametrization, I mean. So the parametrization is made of two lists. One that have the x value here, I close, and here I open the list. So the first curly braces indicate that I will consider a list. In this list, I have two sublists, one for the curves with x positive and one with the for the curves with x negative. Finally, I will tell Mathematica that k will range from 20 to 25 in steps of 0.5. So these levels is the definition of the level curves, the parametrization of the level curves. Shift and enter, and I have them there. Well, now that the list is generated, we would like to visualize them, lift it up in a space. How? With parametric plot 3D. And this visualization will give us an idea of the graph of f. So I will define the following curves. Lift it up equals, and I will define parametric plot 3D. I will define this visualization with parametric plot 3D. And what is what I want to visualize? The level curves I defined previously. This is levels. When I start writing levels, it gives me, it suggests me to use the definition I have recently defined. So I press enter, and then I will specify the parameter y that ranges in between -2 and 2. And I want this visualized within a region, a three-dimensional space region, and I will use plot range. I think I used before. I will copy from above. Here. Here it is. Okay. Well, now shift and enter. And there I have them. These are the curves lifted up on the surface. Of course, we still don't see the surface. The surface is the graph of f. And to construct now or visualize the graph of f, let's see the following definition. If f is a function of two variables with domain D, then the graph of f is the set of all points x, y, and z in R cubed such that z is equal to f of xy, where x and y belongs to D. And to visualize a graph of a two variables function, Mathematica uses plot 3D. So the syntax of plot 3D is simple. You type plot 3D in between brackets, the function that is 25 minus x squared, and the range of variation of the variables, x and y. The function is a function of two variables, despite the fact that y is not shown there in that expression. But we need now to specify the range of variation for x and y. So we will put -2 to 2, comma, y, -2 to 2. Shift and enter. Here it is, the graph. I will define this graph as surface. And I will add the option mesh, none. Because Mathematica automatically adds a mesh when constructing a surface. But well, I will remove this mesh because I will visualize altogether the surface and the curves lifted up. Okay, how I will visualize this? With the command show. When you want to show graphics combined in a single visualization, you use show. So here I use show. That's why I have defined the previous graphs. The one of the curve lifted up, I called on purpose curve lifted up, and the one of surface, I called on purpose surface. But I'm doing this wrong here. And here we have it, the visualization of the curves lifted up on the surface. What we see here is the graph of f and the traces of f within the horizontal planes z equals k. For each curve, you have a different value of k for each straight line. Where k is the height ranging from 20 to 25. It is important to clarify that the level curves are on the xy plane. This is, they are the projection of these traces on the plane z equals 0. To end with this exercise, we will visualize the level curves together with the graph of f and these traces. For this, we will need to modify a little bit the syntax of levels that we defined before, so that we have the level curves on the xy plane. So now let's start by copying and pasting the syntax of levels here, paste below. Here it is. As here, let's change the definition of levels to levels 0. Why level 0? Because I associate this with the plane z equals 0, and the value of z here will be 0. So I want the curve listed at projected on the plane z equals 0. So here 0 and here 0 again. So this new list will give me the parametrizations of the curves projected on the plane xy. And as I don't want to see the result of this, I will add a semicolon like this. And Mathematica does not show me the result. Now, I would like to use parametric plot 3D to visualize this. These are the list of curves on the xy plane, level 0. These are the parametrization. But to visualize them, I need to use parametric plot 3D. So I will define, enter, and I start typing the new definition, that is curves on the xy plane. Pulse, parametric plot 3D, and I will copy and paste from the previous syntax here. But now pay attention that the list is levels 0. The parameter is the same, y, and as I would like to distinguish these curves that are on the xy plane with another color, I would like to distinguish them from the curve lifted up. I will use another option, that is plot style. Plot style and the color red. Here it is. Well, again, I don't want to see this result, and I want to see all together combined in one single visualization. So if I don't want to see the result, after the bracket, I add semicolon. And now, with enter, I use show, and all that I want to see. What is what I want to see? Curves lifted up that I have already defined, and it appears there. As I didn't press Shift Enter yet, level 0 is not, it does not appear when I start typing. When I start typing levels, it only appears the one that is defined, that is levels, not level 0. So levels 0. And you see that it appears in blue when Mathematica has used it. It appears in black. And curves on the XY plane. Now, Shift and Enter. Here, the message that appears is because I typed level 0 rather than levels. Okay. Probably there is another problem here. Show curves lifted up. level 0, and curves on the XY plane. Everything seems to be correct, but not combine the graphics object. Let's see why. Where the problem is. On the XY plane is the same as it appears here. Levels 0. Curve list data level 0. The problem is that I put level 0 and level 0 is a list. It shouldn't be here in show because show is used for combining graphics and level 0 is a list. So here is a mistake here. Level 0, not there. I would like to show what? Curve lifted up, curves on the XY plane, and the surface. Now, yes, very good. Very good, not very good, because I don't see the curves on the XY plane. Why? Because I'm using the plot range value for Z in between 20 and 25. So I will change it from 0 to 25. 0 from 0 to 25. I have done that on curves on the XY plane, but I need to do it also on show here. Very good. Now, yes. And here we see. See? Curves on the XY plane, the level curves. The blue ones, they are that are lifted up, the traces of the surface with the corresponding planes. And if you think that these curves are too thick, you can add an option that is thickness. That option goes together with plot style there, like this. Plot style, red. Now I use curly braces and I put red and then the thickness. Thickness, and in between brackets, value that could be a thin line is 0.01. If you are interested, you can go to the documentation center and you browse thickness and see you investigate how it works in detail. And there it is. It is much thinner than this one. Okay. Well, so here they are. In order not to lose our sense of orientation, let's name the coordinate axis with the option axis label. So let's add here. I will just copy the last part, the one that says show. And here we add axis label to show where we are. Axis label, and in between inverted commas, the name of the axis. Y and Z. Shift and enter. Okay. Well, in this exercise, we have seen a complete demonstration of level curves. We will end this first part of this video here and resume later with exercise B. Thanks for watching.